All right, we're going to take a look at trapezoid sums. We've already seen rectangular sums with LRAM, RRAM, and MRAM. And a better method to come up with an approximation is often using trapezoids instead. So that's what we'll take a look at right here. So for some context, if we need to find the area under the curve, using integrals and the antiderivative is going to give us the exact answer. So if we can do that, that's always the way to go. But there are many cases where that's not a possibility. Sometimes we have a function that's too complicated to find the antiderivative, in which case we can use rectangular or trapezoidal sums. And sometimes in real life data, we just get measurement points, and so we don't have an actual function at all. And so the best we can do is use an approximation, such as rectangles or trapezoidal sums. Okay, so first take a look at the area of a trapezoid, just to remind ourselves. If we label all these sides here, then our area is 1/2 of the sum of the two parallel sides times the width of the trapezoid. Okay, so if we take a look at this curve right here over the interval from 0 to 4, we could find the actual area of the curve by taking the antiderivative, evaluating from 0 to 4, and we get 6.6 repeating. So that's the true area. If we had approximated this using left-hand sums, we could find the heights of each of those rectangles at their left-hand corner, add them all together, and we get 5.75, which is a lower approximation. If we use right-hand sums, this will give us an upper approximation. If we average the two together, that gives us an even better approximation, 6.75, which is pretty close to our 6.6 repeating. And it turns out that that method of averaging the two rectangles would give us trapezoids. So we can, instead of finding two sets of approximations, we can just use trapezoid sums. Right, so our trapezoids each have a width of 1 unit. We take 1/2 times the sum of the two parallel sides. And that gives us our approximation of 6.75. If we have a trapezoid with intervals of equal width, so if every trapezoid has the same width, we can use this trapezoid formula right here, h over 2, where h is the width of the subinterval, times the sum of all of the y values at each of the ends of the subintervals, counting the left endpoint once, the right endpoint once, and everything in between twice. Now, often we don't have subintervals that are all the same width, so we can't use the trapezoid rule. We can only use that if the subintervals are all the same width. So if we had something like this, we have velocity taken at these different times, at 0, 8, 11, 17. So our first subinterval has a width of 8, and then we have 3, and then we have 6. They're not the same, so we can't use that formula. All we can do here is just find the area of each of these trapezoids independently. So if we graph this to get an idea of what that looks like, that first trapezoid has two sides of 34 and 65 with a width of 8. Our second trapezoid has sides of 65, 67, and a width of 3. And our final trapezoid has sides of 67 and 43, and a width of 6. And if we simplify that all down, we end up with a total distance traveled approximately of 924 feet.